Hello, didn't see you there. Or did I? This week on Physics Busters, we tackle everything from frame of reference to propulsion with your hosts, Mr. Momentum and Dr. Decibel. And yours truly, Professor Proton. Without wasting too much time, let's jump in, shall we?
Science ho!
So what's up first on the roster, Dr. Decimal?
I don't know. Let's find out using our state-of-the-art picture show monitor. Interesting. But what's wrong?
Take the next 10 seconds and discuss with your classmates.
That is absolutely correct. The problem has to do with the conservation of angular momentum. Care to explain, Dr. Decibel?
Of course. The initial angular momentum equals the final angular momentum. The initial rotational inertia times the initial angular velocity equals the final. The rotational inertia is mr squared because we're going to treat this as a particle, times v over r, which is the conversion factor for angular velocity, equals the final of those same values. We can cancel out the r's, leaving mrv on both sides. So mr initial times v initial equals mr final times v final. And because we know that these are inversely proportional, r and ri is less than rf, then vi must be greater than vf. Therefore, when I extended my arms, I should have slowed down instead of speeding up.
Thanks for that, Dr. Decimal. I think you guys will enjoy the next clip.
Correct. This problem concerns friction.
Care to explain, Mr. Momentum?
I'd be delighted to. Let's start off by drawing a free body diagram. We've got our normal force, the force of gravity, and of course the force that Sean exerts on Marcus. Now the one force that the video neglects to mention, however, is the force of friction. Now, the force of friction is mu times the normal force, or the friction coefficient times the mass times the gravity. Now, I'm sure that a grassy lawn isn't going to have a friction coefficient of 0, and although Marcus is a strapping young gentleman, I'm sure he doesn't weigh absolutely nothing. I've got a feeling that the force of friction is going to be a bit greater than 0 as well, meaning that Marcus would not slide continuously throughout the field.
That's all alright, but what about this next clip?
Correct. This problem has to do with momentum.
Care to explain, Professor Proton?
Well, of course. Let's go to linear momentum. P initial equals P final. Mass initial, velocity initial equals mass final, velocity final. Now, what's wrong in the video is that the final velocity is not similar to the initial velocity, so we must assume that our masses are similar to go back to the original equation and cross those masses out. This will tell us that the initial velocity should be similar to the final velocity.
This next clip ought to tickle your fancy. Indeed, this problem revolves around projectile motion. Dr. Decimal will provide further detail.
The bullet will be shot from the gun with a very large x velocity and a y velocity of 0. The shell, being shot outwards at an x velocity, will also have a y velocity of 0. Using the kinematics equation x equals x naught plus vyt plus 1/2 at squared, we'll find out that the time it takes for the shell to reach the ground and the bullet to reach the ground will be the same, because the initial y velocity and final x position are both 0, and they both accelerate to the ground at 9.8 meters per second per second.
This next clip needs no introduction, so I will not introduce it. Correct. This problem deals with air resistance. Care to explain, Mr. Momentum?
Sure thing. In the video, the force of gravity is a constant. On the other hand, the force of air resistance continues to increase until it surpasses the force of gravity and in turn forces me to change direction and head upwards. However, this is not the case in reality. What actually happens is that the force of air resistance continues to increase until it matches the force of gravity. This natural phenomenon is called terminal velocity, which is the constant speed that a falling object eventually reaches.
I've often dreamt about performing the contents of this next clip myself.
Put your records on. Tell me your favorite song. You go ahead, let your head.
Correct. This has to deal with the conservation of angular momentum and elliptical orbits. Allow me to explain.
As you can tell, Chance is flying around Earth in an elliptical orbit. At the point closest to the Earth, it is called the periapsis, and at the other end, where it's farthest away from the Earth, is called the apoapsis. To find out what Chance is doing wrong, we'll use the conservation of angular momentum. The initial rotational inertia times the initial angular velocity equals the final. We will assume that Chance is a particle and simplify the equation to mRIVI equals mRFVF. Because the periapsis is the initial position and the apoapsis is the final, he should be going faster with a shorter radius due to R and V being inversely proportional, unlike in the video.
This next clip does the heart good.
I'm gonna go to space.
Okay.
I'm a rocket man, burning out his fuse out very long.
Hey, for the sake of science, what time is it?
12:05. 10 years ago.
Great Scott. Interesting. I'll leave the specifics to Professor Proton.
Well, of course. Let's go to Einstein's theory of special relativity with a famous thought experiment, how the light pulse moves two different distances based on your frame of reference. It forms a triangle based on with the two frames of references combined. And we go to good old Pythagorean and we find the real solution to time dilation going near the speed of light. The problem with the video is that it brings you back in time, and that will never happen. Here is the equation for time dilation, but time will always just stretch out for different frames of reference, never go back.
Thank you for joining us on Physics Busters. See you next week.
So what did you two think about those recent science discoveries?
I feel like I should do this top button too.
Yeah.
Oh wow, that's a stretch. Uh-oh. I'm gonna be holding my breath this entire time.
A quark is a fundamental constituent of matter, observed in 1968 through deep elastic scatter. We found that protons aren't as simple as we thought. We thought they were solid particles, but they are not. Protons, in fact, are made up of 3 separate pieces. It just gets more confusing as our knowledge increases, but that is what a quark is. It's a piece of a proton, and they also make up other things, including a neutron. Oh, up, down, strange charm, top, bottom. If you don't know what a quark is, it don't matter, you still got them. And with leptons and bosons, unless something's amiss, they make up everything that we can see and that we know exists. Things made up of quarks, including protons and neutrons, are composite particles that physicists call hadrons. Many types of hadrons are theoretically described.